Welcome to this video on forces at a point. It is one of several videos in a short course on equilibrium posted at terje.civil.ubc.ca, Toolbox, a website that contains notes, examples, and algorithms for structural analysis. Please visit the website for more videos and other material relevant for this course. This video has three objectives. The first is to extend the concept of a resultant force. Instead of the distributed load considered in the previous video, the situation on the left-hand side has two forces, F1 and F2, acting at a point. In general, there could be more than two forces. That point will feel the same if we replace the forces with one single resultant force, denoted by R. It is an objective in this video to learn how to determine such resultants. The second objective addresses the opposite situation. As shown on the right-hand side, we now start with one single force, denoted by R. The objective is to determine the horizontal and vertical components of that force. The third objective is to employ the two previous topics in order to enforce equilibrium at a point. Two examples of when that might be useful are shown on this slide. On the left is a truss. A structural engineer would want to know the forces in each member of the truss due to the two external loads that are acting. To accomplish that, the engineer imposes equilibrium at every joint of the truss. That is one example of equilibrium of forces at a point. On the right-hand side is another example. This is a frame structure, which we will learn more about in other videos. The point now relates to the joints of the frame. The structural engineer might want to check that the forces at each joint are in equilibrium. Alternatively, the engineer uses equilibrium at a joint to determine unknown forces there. In short, this slide shows examples of the consideration of equilibrium at a point. The next slide shows the equilibrium equations that we use. The situation is simple. Equilibrium in the horizontal direction, here called the x direction, means that the sum of all forces that act in the horizontal direction must equal 0. That means the forces acting towards the left must be matched by the forces acting towards the right. Similarly, equilibrium in the vertical direction, here called the y direction, means that the sum of all forces that act in the vertical direction must equal 0. That means the forces acting downwards must be matched by the forces acting upwards. It is possible, and often preferred by many engineers, to establish these two equilibrium equations directly. However, a graphical approach also exists and is included in this course. The graphical approach addresses both equilibrium equations shown here at once. The next slide shows an overview of the approaches. The left-hand side starts with the notion of finding the resultant of two or more forces. That can be used by itself, without any considerations of equilibrium, in order to find a force resultant. However, it can also be used in a graphical approach in order to establish equilibrium by enforcing that the resultant must be 0. The right-hand side of this slide shows that the ability to determine the horizontal and vertical components of forces led directly to the trigonometric approach for equilibrium of forces at a point. Once all horizontal component of all the forces are determined, they are summed and set to 0. Similarly for the vertical components. The next slide introduces the graphical approach, which is a way to determine the resultant of two or more forces. The left-hand side shows two forces acting at a point. The forces are called F1 and F2. The methodology is this. Place the forces graphically on paper, one after another. Make sure that the tail end of one force follows the arrow end of the previous force. Also make sure that the orientation of the force is kept, and that the length of the arrow is proportional to the magnitude of the force. That is done in the top portion of this slide. F1 is first put down on paper. Then F2 is made to follow F1. The resultant force that we are seeking is always the force arrow that goes from the start point to the end point of the arrows. This means that we have now obtained this resultant force R. Alternatively, the bottom portion of the slide shows what happens if F2 is first put down on paper followed by F1. Again, the resultant force we are seeking is the force arrow that goes from the start point to the end point of the arrows we have laid out. Carefully notice that we now obtained exactly the same resultant force. In other words, the order in which we lay out the forces does not matter. The next slide shows a similar example, just with more forces. The approach is identical. First, we identify in the leftmost figure which forces are acting at the point. Next, we lay out all the forces, maintaining their orientation and letting the length of each arrow be proportional to the magnitude of the force. What ultimately closes the force polygon, or more precisely, what connects the start point with the end point, is the resultant force that we seek. The resultant force, R, shown on the right, is equivalent to all the forces on the left acting on this point. The next slides take the step of using the graphical approach to either check equilibrium or to utilize equilibrium for the purpose of determining unknown forces. Remember, equilibrium at a point means that there is zero resultant force there. In other words, equilibrium requires the balance of forces. To the left is shown 5 forces acting at a point. We wish to know whether these are in equilibrium, or the joint is moving somewhere with constant acceleration as Newton postulated. In the graphical approach, we lay the forces out on paper, one by one, which is done on the right-hand side. F1 is arbitrarily sketched first, arbitrarily followed by F4, F5, F3, and F2. Interestingly, the flow of forces ended up at the same point as we started from. What does that mean? It means that the forces at this point are in equilibrium. In other words, the resultant force is zero. The next slide also employs equilibrium, but the objective is different. In this case, there are 3 known forces acting at a point. Those forces are shown with thick solid lines. We also know the direction of 2 additional forces that may act at the joint, shown as dashed lines, but we do not know their value. For that reason, we do not know the length of the 2 dashed lines. Carefully note that we can have 1 or 2 unknown forces, as in this case, but we can never have more than 2 unknown forces at a joint when we tried to determine the unknown forces. Implicitly, we are using horizontal and vertical equilibrium. That means we have 2 equations behind the scenes, so we can only determine 2 unknown forces. This is a typical situation in the analysis of trusses. We know that members come into a joint from certain directions, but we do not know the value of the force in those truss members. On this slide, we are still in the business of using the graphical approach, so we start by laying out the known forces on paper. That is shown with the solid black lines here. Next, we try to close the force polygon by using the directions set by the unknown forces. Here we see that the horizontal and inclined force directions allow us to close the force polygon. A closed force polygon means that the forces are flowing continuously around it like a river of forces. That continuous flow also determines the length and the direction of the arrows. That information is directly translated to the rightmost figure, where all the forces are now drawn. Notice that the direction of the arrows are taken directly from the closed force polygon. Also notice that both red arrows, namely both the unknown forces, represent compression because they push at the joint, instead of pulling at it. The next slide briefly outlines the trigonometric approach for checking or using equilibrium. We start by decomposing all forces into their horizontal and vertical components. Next, we explicitly write out equilibrium in the horizontal direction and equilibrium in the vertical direction. There will be more examples in the videos on analysis of determinate structures. Thanks for watching this video. Please visit terje.civil.ubc.ca Toolbox for more videos and more material relevant for the modern structural engineer. See you soon.